Greetings everyone, welcome to today's video. I'm Clifford Mwenda, GMAT trainer with the KNLEF program. And noticeably with the recent changes to the GMAT exam, we have the new GMAT Focus Edition. Comparing both GMAT Focus Edition and the GMAT Classic Edition, we had the likes of geometry in the Classic Edition, now it's not there. But for probability, we still have probability for both Classic and Focus Edition. And I hope this video is insightful and fun, exciting to all Focus Edition test takers and Classic Edition test takers. And so, without much further ado, let's jump into the video. We'll be looking into a probability, specifically these probability events. We understand we have some terms that most of us are not familiar with, and we'll be looking into that as soon as possible. And so, let's jump in. First, I will start off with an event. What is an event, really? An event is a set of an experiment possible outcomes. For example, if you roll a six-sided die with faces numbered 1 to 6, this is an experiment with 6 possible outcomes, right? And looking into the face that faces up, and we check the number that is on that face, those are the outcomes. We have 1, 2, 3, 4, 5, and 6. All right. One event in this experiment is when the outcome is 1, when you throw this die, and 1 is on the top of the top surface, and this is written as curly brackets and 1 inside. All right. Another event is an experiment where the outcome is an even number. From 1 to 6, we have 2, 4, and 6. And this event has 3 outcomes, the 2, 4, and 6, and it is written into curly brackets 2, 4, and 6. All right. There are outcomes in an event, all right? And an event is a set of an experiment's possible outcomes. I hope that's clear. Now, let's jump into probability with respect to this event. A probability of an event E, denoted as P into bracket E, that's probability of E, ranges from 0 to 1. And it's 0 when the event cannot happen. It's impossible for the event to happen, all the way to 1 when the event is certain and it must happen. All right. And in an experiment where outcomes are equally likely, the probability of the event E, that's P into bracket E, is the total number of outcomes in E, right? The outcomes in E. And we call these are the successes all over the total number of possible outcomes. All right. And if X is a subset of E, that is, the outcomes in X are also in E. Maybe they're the same, maybe they're less. If X is a subset of E, then the probability of X is less than or equal to the probability of E. All right. And that's how we calculate the probability of an event E. And we'll just look into a general guide that we'll be using for combination or counting methods and probability as well. You can keep this in mind and it will help you a lot, where OR means add and AND means multiply. And this comes about when you're doing some calculation and you have to put the word in your head and say, I need X or Y. Then now that you're dealing with addition or subtraction, and if you're dealing with X and Y, then you know that you're dealing with multiplication. All right, so that's the OR rule and the AND rule. Say we have these 2 events, X and Y, only X and Y. Now the events, then probability of X not happening is 1 minus probability of X, which is probability of Y, since we have only 2 events, all right? And probability of X not happening being equal to the probability of Y happening, that is the complementary rule, and it can be used when you're dealing with keywords such as at least. And find that doing the failures is much simpler and much more efficient than doing the successes. Then you have to deal with the failures and subtract that from the 1, that's the probability of the total certainty in that say events, and then find the successes that you want. All right, then you have the probability of X or Y. In this case, this is the probability given that you have a set X and a set Y. This is the union, all right? The union of X and Y. The probability of X or Y, that's probability of X plus probability of Y minus probability of X and Y. And this is what we call the intersection. So if you need X or Y, then subtracting whatever outcomes are common in both set X and Y, then find addition of X and Y, right? Those outcomes in X, those outcomes in Y, subtract those that are common in X and Y so that can have probability of X or Y. Then you have probability of X and Y, that's the intersection that I'm talking about. And for independent events, we have probability of X times probability of Y in this case. And that actually depends with the type of events, and we'll be talking more about these events in the next slide. So if you have an event, independent event, then probability of X and Y is probability of X times probability of Y. Let's look into these events and how these two general formulas are used while tackling probability questions. What are these types of events? We have the mutually exclusive events, we have the independent events, and dependent events. Let's look into the mutually exclusive events, or also known as disjoint events. So if events E and X are mutually exclusive or disjoint events, then events E and X cannot occur at the same time, rather. For instance, if you have a coin and flip it, the coin will only fall heads or tails. You can't have both, right? That's what we mean by mutually exclusive or disjoint events. And for this case, since they can't happen at once, we have a scenario whereby you have two circles and there's no overlapping here. And that's why we call this intersection between E and X cannot happen. That's 0. So probability of E and X equals to 0. And reverting back to this OR rule, we have probability of E or X, then will be probability of E plus probability of X. Should be minus probability of E and X, but in this case it's 0, so it remains like that. That's how you do mutually exclusive events. If you're asked about probability of E or X, then you have probability of E plus probability of X. If you're asked about probability of E and X, which is rarely asked about, if they're mutually exclusive, that is just 0. All right, now let's look into independent events. We have if events E and X are independent events, then the events can happen at the same time. There's an overlap. Happens like that. There's an overlap here. All right, can happen at the same time. But the occurrence of an event, that, for example, in this case, the occurrence of event E does not affect the occurrence of event X. And the occurrence of event X does not affect the occurrence of event E. That happens when, you, for example, you have two fair coins. Now we flip two fair coins and not one. The outcome of one fair coin does not affect the outcome of the other fair coin. All right. So having a head doesn't tell you that you'll have tails for the next one. If you have a tails here, it doesn't tell you you'll have another tail on the other coin. So in this case, probability of E and X rather equals to probability of E times probability of X. There's an intersection, and that is what we did for the previous example. These are independent events, and then we'll have probability of E or X will be probability of E plus probability of X minus the probability of E and X. And this is more of the set theory addition rule. So you can go and look into that. We have a video on sets. You can go on and watch that video. If events E and X are dependent events, now we're dealing with dependent events or conditional events. The other terms we have for these, and these events can occur at the same time. And the occurrence now of event E affects the occurrence of X, and vice versa can also happen, where you have event X happening affects the occurrence of event E. All right. Therefore, in this case, we have probability of E and X will be probability of E times probability of X, given that E has already happened, and or probability of X times probability of E, given that X has already happened. And in this case, probability of E or X will be probability of E plus probability of X minus probability of E and X. But in this case, this part here is this conditional probability of E and X. Now, I'll give an example. For this case, we have 3 green balls, and 5 black balls. Now, what's the probability of having black for the first try, first pick, black for the second pick, black for the third pick, and in this case, without replacement? In this case, if you have a keyword like without replacement, now you're dealing with dependent events, and you have to think critically and move on logically. Putting in mind you're dealing with conditional events, let's look into how this event, doing this event affects the other event. Now, let's look into picking the first black ball. If you have 5 black balls and 3 green balls, you have a total of 8 balls. And out of these 8 balls, we are picking the first black ball. Now, we have the probability of picking a black ball for the first try is 5/8. Now, we already picked one. We're not replacing the black ball. We have 7 balls left for the second pick. Now, for the second pick, we have 4 black balls now. The probability of picking another black ball is 4 now. Times, we've picked 2 black balls. We are left with 6. And we are left with 3 black balls as well. And we'll have, for the third pick, 3/6. And for this, we'll have 5/8 times 4/7 times a half. A factor of 4, 1, a factor of 4, 2. This is 7 times 4, which is 28. And 5 times 1 times 1, that's 5. And then probability of picking a black ball for the first try, black ball for the second pick, and black ball for the third pick is 5/28. All right, and that's how we deal with the dependent conditional events.
You're watching Success with Bob Mwiti Show, presented to you by Upstack America. Upstack America is a consulting company that helps immigrants find amazing higher education and job opportunities in the tech industry in the United States. You can find our programs by going to www.upstackamerica.com. Upstack America, we wake you up to the unlimited potential.
Let's look into practice questions. We can pause the video and give this a try, and then we can see how we can approach this one. What is the probability of rolling 2-sided die and getting snake eyes? Snake eyes is when we have our 1 on the top for both dice. Just like that, yeah. Now, what we want is for the first die, we want a 1, and second die, we want a 1 as well. What's the probability of having 1 for the first one? That's 1/6. Probability of having 1 on the second one is 1/6. These are dependent, not dependent, but independent events. And throwing one die doesn't affect the outcome of the other die. Therefore, and yeah, it's and, right? We have to have a probability of having 1 and having another 1 in the other die. So we multiply this together, 1/6 times 1/6 equals to 1/36. The trick behind, the reasoning behind this probability questions is, once you get the idea and the logic behind whatever is being asked in that question, then the calculation bit is much simpler. It's just using your critical thinking. How well can you paraphrase the question? How well can you put your attention to the right detail? Yeah, and how well you can recognize these patterns, and you can answer these questions much faster. Let's have a dependent situation here and see how we can tackle this question. Yes, please pause the video and give this a try. If there are 3 girls and 2 boys on a team, we have 3 girls, 2 boys on a team, and 2 members of the team are randomly selected. We're picking 2 members of the team. Then what's the probability that at least, see that keyword, and this at least calls in for a complementary rule in case the traditional approach is much harder. What is the probability that at least 1 girl will be selected to the team? What do we want? We want a situation where we have, if you pick the first boy, we have a second girl. If you pick the first girl, we have boy, and if you have both as girls, at least one, right? If you pick the first one as boy, then you have 3/5 for the first one, and the second pick will be a girl. Yeah, the first one, sorry, is 2/5 rather. 2/5 since we're picking our boys out of the total team. So we have 2/5 total outcomes, successes. Yeah, I hope you can remember that. Then for the second pick is girls. Now we have 3 girls left and one boy left. So we have a total of 4 in this case. Second one, we have 3 girls out of 5 for the first pick. We're left with 4 members. Then we're picking a boy for the second one, that's 2. And the third one, we have 2 girls. So the first pick, we have 3/5. And second pick out of 4, we are left with 2 girls. And now we have to add all of this since we need probability of having boy girl or probability of having girl then boy or probability of having a girl then and a girl. So we multiply this. This is 6 out of 20. This is 3/10. This is a half here. So 3/10 as well. This here is also a half, and this is 3/10 as well. Add these 3 together, that's 9/10. All right, that's the probability of having at least one girl that will be selected from the team when you're picking this, randomly picking these 2 members out of three girls and 2 boys. Right now, that's the traditional approach. What if we try to find the failures, the things that we don't want, and subtract from the total? That's 1. What don't you want? We don't want a situation where we have a boy and a boy, right? If you don't want this, let's find probability of having a boy and a boy. For the first pick, we'll have 2/5, and the second pick will be left with 4 members, and we'll have to pick one boy out of the 4, and that will be 2/20, and that should be 1/10. This is something that we don't want. Subtract this from 1, and then we'll have what we want and what we're looking for. 9/10, 9/10, and you can see much simpler, much more effective, depending on how you can understand the question and how well you find which approach actually is simpler for you, more efficient for you. All right, I hope I got that question right. Now let's look into some other practice for the day. Right, in an experiment with events A, B, and C, and suppose that you have probability of A equals to 0.23, probability of B 0.40, and probability of C 0.85. And I have probability of A 0.23, probability of B 0.40, and probability of C 0.85. Also suppose events A and B are mutually exclusive. If A and B are mutually exclusive, then that means probability of A and B will be 0, and probability of A or B should be probability of A plus probability of B. Since probability of A and B is 0, so probability of A, that's 0.23. Probability of B, that's 0.40. When we add this together, that should be 0.63. Right? I understand you can do this, you can answer the question just straightforwardly, but we need just to understand more on this question. We have a probability of A or B as 0.63. Now let's continue. We have events B and C are independent. If B and C are independent, then probability of A and B should be a probability of A times probability of B. And this is a probability of A, that's 0.23. No, we're dealing with B and C rather. All right, let's have B and C. Probability of B and C are independent, therefore we have probability of B times probability of C. Probability of B is 0.40, and probability of C, that's 0.85. With 4 decimal places, you can check 40 times 85, and this will have 20 times 170, and multiplying this is 34 and 2 zeros. We have 4 decimal places and put that at 0.34. This is 0.34. Then probability of B or C, this will be probability of B plus probability of C minus probability of B and C. And this will be probability of B, that's 0.40. Probability of C, that's 0.85, minus probability of B and C, that's 0.34. Let's simplify this, 0.06. I'm taking this minus this, then plus 0.86. This is 1, this is 9, and this is 0.91, right? We've deducted probability of B or C, probability of A or B. Now, are events A and C mutually exclusive? If events A and C are mutually exclusive, then we should have probability of A and C as 0. And if that's 0, then probability of A or C should be less than or equal to 1. All right. From this, we know that probability of A or C, this is probability of A plus probability of B. That's if they are mutually exclusive. Then add a probability of A, that's 0.23. Probability of B, that's 0, not B, but C. Rather, probability of C, that's 0.85. And that should be 8, 10, 1.08. As you can see, this 1.08 is greater than 1. That's the total probability that you can have, really. And therefore, for a probability of A or C to be mutually exclusive, we need to have this less than or equal to 1. But since it's greater than or greater than 1, that implies that the A or C are dependent or independent events. They cannot be mutually exclusive since the probability is greater than 1, and you need probability of A and C to subtract from 1.08 so that you can have a value less than or equal to 1. All right. And as you can see, basically these events are key areas that you need to master so that you can approach these questions much more effectively. So I've been Clifford Manager on the Kenya Leap program, and yeah, thank you all for coming for today's video. Thank you all for watching this video. Please like, subscribe, and share this content. If you have any inquiries or comments or recommendations, please put it in the comment section below. See you till the next video. Bye bye.